Lecture 3 Dynamics. Lenny. What makes things move, George? George. Forces do, Lenny. Lenny. What makes things stop moving, George? George. Forces do, Lenny. Aristotle's Law of Motion. Aristotle lived in a world dominated by friction. To make anything move, a heavy cart with wooden wheels, for example, you had to push it, you had to apply a force to it. The harder you pushed it, the faster it moved. But if you stopped pushing, the cart very quickly came to rest. Aristotle came to some wrong conclusions because he didn't understand that friction is a force. But still, it's worth exploring his ideas in modern language. If he had known calculus, Aristotle might have proposed the following law of motion. The velocity of any object is proportional to the total applied force. Had he known how to write vector equations, his law would have looked like this. Vector F equals mass times vector V. Vector F is of course the applied force, and the response, according to Aristotle, would be the velocity vector V. The factor m relating the two is some characteristic quantity describing the resistance of the body being moved. For a given force, the bigger the m of the object, the smaller its velocity. With a little reflection, the old philosopher might have identified m with the mass of the object. It would have been obvious that heavier things are harder to move than lighter things, so somehow the mass of the object has to be in the equation. One suspects that Aristotle never went ice skating, or he would have known that it is just as hard to stop a body as to get it moving. Aristotle's law is just plain wrong, but it is nevertheless worth studying as an example of how equations of motion can determine the future of a system. From now on, let's call the body a particle. Consider one-dimensional motion of a particle along the x-axis under the influence of a given force. What I mean by a given force is simply that we know what the force is at any time. We can call it capital Ft. Note that the vector notation would be a bit redundant in one dimension. Using the fact that the velocity is the time derivative of position x, we find that Aristotle's equation takes the form dxt by dt equals ft by m. Before solving the equation, let's see how it compares to the deterministic laws of chapter 1. One obvious difference is that Aristotle's equation is not stroboscopic, that is, neither t nor x is discrete. They do not change in certain stroboscopic steps. They change continuously. Nevertheless, we can see the similarity if we assume that time is broken up into intervals of size delta t and replace the derivative by delta x by delta t. Doing so gives xt plus delta t equals xt plus delta t ft by m. In other words, wherever the particle happens to be at time t, at the next instant, its position will have shifted by a definite amount. For example, if the force is constant and positive, then in its incremental step, the particle moves forward by an amount delta t ft by m. This law is obviously deterministic. Knowing that the particle was at a point x0 at time t equals 0, or simply x0, one can easily predict where it will be in the future. So by the criteria of chapter 1, Aristotle did not commit any crime. Let's go back to the exact equation of motion. The derivative of xt with respect to time equals ft by m. Equations for unknown functions that involve derivatives are called differential equations. This one is a first-order differential equation because it contains only first derivatives. Equations like this are easy to solve. The trick is to integrate both sides of the equation. Integration of dx by dt with respect to dt equals integration of ft by m also with respect to dt. The left side of the equation is the integral of a derivative. That's where the fundamental theorem of calculus comes in handy. The left side is just xt plus c. The right side, on the other hand, is the integral of some specified function, and apart from a constant, is also determined. For example, if f is a constant, then the right side is f by mt plus c. Now that we included an additive constant, putting an arbitrary constant on both sides of the equation is redundant. In this case, the equation of motion is satisfied by xt equals f by mt plus c. How do you fix the constant c? The answer is by the initial condition. For example, if we knew that the particle started at x equals 1 at time t equals 3, we would plug these values in, obtaining 1 equals f by m3 plus c, and solve for c. This gives us c equals 1 minus 3 f by m. Exercise 1. Given a force that varies with time according to F equals to t square and with the initial condition at time 0, x0 equals pi, use Aristotle's law to find xt at all times. Aristotle's equations of motion are deterministic, but are they reversible? In lecture 1, I explained that reversible means that if all the arrows were reversed, the resulting new law of motion would also be deterministic. The analogous procedure to reversing the arrows when time is continuous is very simple. Everywhere you see time in the equations, replace it with the minus time. That will have the effect of interchanging the future and the past. Changing t to minus t also includes changing the sign of small differences in time. In other words, every delta t must be replaced with minus delta t. In fact, you can do it right at the level of the differentials dt. Reversing the arrows means changing the differential dt to minus dt. Let's go back to Aristotle's equation. Ft equals m dx by dt. And change the sign of time, and the result is function f of minus t equals minus m dx by dt. The left-hand side of the equation is the force, but the force evaluated at time minus t, not at time t. However, if ft is a known function, then so is f minus t. In the reversed problem, the force is also a known function of reversed time. On the right-hand side of the equation, we've replaced dt with minus dt, thereby changing the sign of the whole expression. In fact, one can shift the minus sign to the left-hand side of the equation. Minus f minus t equals m dx by dt. The implication is simple. The reverse equation of motion is exactly like the original, but with a different rule for the force as a function of time. The conclusion is clear. If Aristotle's equations of motion are deterministic into the future, they are also deterministic into the past. The problem with Aristotle's equations is not that they are inconsistent, they are just the wrong equations. It is interesting that Aristotle's equations do have an application, not as fundamental laws, but as approximations. Frictional forces do exist, and in many cases they are so important that Aristotle's intuition, things stop if you stop pushing, is almost correct. Frictional forces are not fundamental. They are a consequence of a body interacting with a huge number of other tiny bodies, atoms and molecules that are too small and too numerous to keep track of. So we average over all the hidden degrees of freedom. The result is the frictional forces. When frictional forces are very strong, such as in a stone moving through mud, then Aristotle's equation is a very good approximation, but with a qualification. It's not the mass that determines the proportionality between the force and velocity, it's the so-called viscous drag coefficient. But that may be more than you want to know. Mass, acceleration, and force. Aristotle's mistake was to think that a net applied force is needed to keep an object moving. The right idea is that one force, the applied force, is needed to overcome another force, the force of friction. The isolated object moving in free space, with no forces acting on it, requires nothing to keep it moving. In fact, it needs a force to stop it. This is the law of inertia. What forces do is change the state of motion of a body. If the body is initially at rest, it takes a force to start it moving. If it's moving, it takes a force to stop it. If it is moving in a particular direction, it takes a force to change the direction of motion. All of these examples involve a change in the velocity of an object and therefore an acceleration. From experience, we know that some objects have more inertia than others. It requires a larger force to change their velocities. Obvious examples of objects possessing large and small inertia are locomotives and ping pong balls, respectively. The quantitative measure of an object's inertia is its mass. Newton's law of motion involves three quantities: acceleration, mass, and force. Acceleration we studied in Lecture 2. By monitoring the position of an object as it moves, a clever observer with a bit of mathematics can determine its acceleration. Mass is a new concept that is actually defined in terms of force and acceleration. But so far we haven't defined force. It sounds like we are in a logical circle in which force is defined by the ability to change the motion of a given mass, and mass is defined by the resistance to that change. To break that circle, let's take a closer look at how force is defined and measured in practice. There are very sophisticated devices that can measure forces to great accuracy, but it will suit our purposes best to imagine a very old-fashioned device, namely a spring balance. It consists of a spring and a ruler to measure how much the spring is stretched from its natural equilibrium length. See Figure 1. Figure 1. A spring balance. The spring has two hooks, one to attach to the massive body whose mass is being measured, and one to pull on. In fact, while you are at it, make several such identical devices. Let's define a unit of force by pulling one hook, while holding the other hook fixed to some object A, until the pointer registers one tick on the ruler. Thus, we are applying a unit of force to A. To define two units of force, we could pull just as hard enough to stretch the spring to two ticks, but this assumes that the spring behaves the same way between one tick and two ticks of stretching. This will lead us back to a vicious circle of reasoning that we don't want to get into. Instead, we define two units of force by attaching two spring balances to A and pulling both of them with a single unit of force. See Figure 2. In other words, we pull both hooks so that each pointer records a single tick. 3 units of force would be defined by using 3 springs, and so on. When we do this experiment in free space, we discover the interesting fact that object A accelerates along the direction in which we pull the hook. More exactly, the acceleration is proportional to the force, twice as big for 2 units of force, 3 times as big for 3 units, and so on. Figure 2, twice the force. Let us do something to change the inertia of A. In particular, we will double the inertia by hooking together 2 identical versions of object A. See Figure 3. Figure 3, twice the mass. What we find is that when we apply a single unit of force, by pulling the whole thing with a single spring stretched to one tick, the acceleration is only half what it was originally. The inertia, or mass, is now twice as big as before. The experiment can obviously be generalized. Hook of 3 masses and the acceleration is only a third as big, and so on. We can do many more experiments in which we hook any number of springs to any number of A's. The observations are summarized by a single formula, Newton's second law of motion, which tells us that force equals mass times acceleration. Vector F equals m times vector A. This equation can also be written in the form vector F equals m times the time derivative of vector v. In other words, force equals mass times the rate of change of velocity. No force, no change in velocity. Note that these equations are vector equations. Both force and accelerations are vectors because they not only have magnitude but also direction. An interlude on units. A mathematician might be content to say that the length of a line segment is 3, but a physicist or engineer or even an ordinary person would want to know 3 what? 3 inches, 3 centimeters, or 3 light years? Similarly, it conveys no information to say that the mass of an object is 7 or 12. To give the numbers meaning, we must indicate what units we are using. Let's begin with length. Somewhere in Paris rests the defining platinum meter stick. It is kept in a sealed container at a fixed temperature and away from the conditions that might affect its length. From here on, we will adopt the meter stick as our unit of length. Thus we write x equals length equals meters. Despite its appearance, this is not an equation in the usual sense. The way to read it is x has units of length and is measured in meters. Similarly, t has units of time and is measured in seconds. The definition of a second could be given by the amount of time it takes a certain pendulum to make a single swing. T equals time equals seconds. The units meters and seconds are abbreviated as m and s respectively. Footnote 1. There is a more modern definition of the meter in terms of the wavelength of light emitted by atoms jumping from one quantum level to another. For our purposes, the Paris meter stick will do just fine. Once we have units for length and time, we can construct units for velocity and acceleration. To compute the velocity of an object, we divide a distance by a time. The result has units of length per time, or in our units, meter per second. V equals length by time equals m by s. Similarly, acceleration is the rate of change of velocity, and its units are velocity per unit time, or length per unit time per unit time. A equals length by time times 1 by time equals length by time square equals meter by second square. The unit of mass that we will use is the kilogram. It is defined as the mass of a certain lump of platinum that is also kept somewhere in France. Thus, m, which is mass, equals kilogram equals kg. Now let's consider the unit of force. One might define it in terms of some particular spring made of a specific metal stretched a distance of 0.01 meter or something like that. But in fact, we have no need for a new unit of force. We already have one, namely the force that it takes to accelerate 1 kilogram by 1 meter per second per second. Even better is to use the Newton's law F equals ma. Evidently, force has units of mass times acceleration. F equals force equals ma, which is equals mass times length divided by time square, which is kg meter by second square. This is a name for the unit of force. 1 kilogram meter per second square is called a Newton, abbreviated capital N. Newton himself, being English, probably favored the British unit, namely the pound. There are about 4.4 newtons to a pound. Some simple examples of solving Newton's equations. The simplest of all examples is a particle with no forces acting on it. The equation of motion is equation 2, but with force set to 0. M times the time derivative of vector v equals 0. Or using the dot notation for time derivative, m vector v dot equals 0. We can drop the factor of mass and write the equation in component form as v dot x equals 0, v dot y equals 0, and v dot z equals 0. The solution is simple. The components of velocity are constant and can be just set equal to their initial values. Vxt equals vx0. The same goes for the other two components of velocity. This, incidentally, is often referred to as the Newton's first law of motion. Every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. Equations 1 and 2 are called Newton's second law of motion. The relationship between an object's mass m, its acceleration a, and the applied force F is F equals ma. But as we have seen, the first law is simply a special case of the second law when the force is 0. Recalling that velocity is the derivative of position, we can express equation 3 in the form x dot equals vx at 0. This is the simplest possible differential equation whose solution for all components is xt equals x0 plus vx at 0t, yt equals y0 plus vy at 0t, z at t equals z0 plus vz at 0. A more complicated motion results from the application of a constant force. Let's first carry it out for just the z direction. Dividing by m, the equation of motion is v dot z equals capital Fz divided by m. Exercise 2. Integrate this equation. Hint: use definite integrals. From this result, we deduce Vzt equals Vz0 plus Fz by mt, or Zt equals Vz0 plus Fz by mt. This is probably the second simplest differential equation. It is easy to solve. Zt equals Z0 plus Vz0t plus fz by 2mt square. Exercise 3. Show by differentiation that this satisfies the equation of motion. This simple case may be familiar. If z represents the height above the surface of the earth and fz by m is replaced with the acceleration due to gravity, fz by m equals minus g. Then equation 4 is the equation describing the motion of an object falling from height z0 with an initial velocity vz0. Therefore zt equals z0 plus vz0t minus gt square. Let's consider the case of the simple harmonic oscillator. This system is best thought of as a particle that moves along the x-axis, subject to a force that pulls it toward the origin. The force law is Fx equals minus x. The negative sign indicates that at whatever the value of x, the force pulls it back toward x equals 0. Thus, when x is positive, the force is negative and vice versa. The equation of motion can be written in the form x double dot equals minus k by mx, or by defining k by m with omega squared, that gives us x double dot equals minus omega square x. Exercise 4. Show by differentiation that general solution to equation 6 is given in terms of two constants a and b by xt equals a cos omega t plus b sin omega t. Determine the initial position and velocity at time t equals 0 in terms of a and b. The harmonic oscillator is an enormously important system that occurs in concrete contexts ranging from the motion of a pendulum to the oscillations of the electric and magnetic fields in a light wave. It is profitable to study it thoroughly. Interlude 3. Partial differentiation. Look out there, Lenny. Ain't those hills and valleys pretty?
Yeah, George. Can we get a place over there when we get some money? Can we?
George squinted.
Exactly where are you looking, Lenny?
Lenny pointed out.
Right over there, George. That local minimum.
Partial derivatives. The calculus of multivariable functions is a straightforward generalization of single variable calculus. Instead of a function of a single variable t, consider a function of several variables. To illustrate, let's call the variables x, y, z, although these don't have to stand for coordinates of ordinary space. Moreover, there can be more or fewer than 3. Let us also consider a function of these variables, capital V, as a function of variables x, y, and z. For every value of x, y, z, there is a unique value of v, x, y, z that we assume varies smoothly as we vary the coordinates. Multivariate differential calculus revolves around the concept of partial derivatives. Suppose we are examining the neighborhood of a point x, y, z, and we want to know the rate at which v varies as we change x while keeping y and z fixed. We can just imagine that y and z are fixed parameters, so the only variable is x. The derivative of v is then defined by dv by dx equals the limit delta x tending to 0, delta v by delta x, where delta v is defined by delta v equals v at x plus delta x, y, z minus v at x, y, z. Note that in the definition of delta v, only x has been shifted, y and z are kept fixed. The derivative defined in equation 1 and 2 is called the partial derivative of v with respect to x and is denoted by del v by del x. Or when we want to emphasize that y and z are fixed, we write del v by del x subscript y z. By the same method, we can construct the partial derivative with respect to either of the other variables. dv by del y equals limit delta y to 0, delta v by delta y. A shortened notation for the partial derivatives of v with respect to y is del v by del y equals del y v. Multiple derivatives are also possible. If you think of del v by del x as itself being a function of x, y, z, then it can be differentiated. Thus, we can define the second order partial derivative with respect to x. Del square v by del x square equals del x, del v by del x equals del xx v. Mixed partial derivatives also make sense. For example, one can differentiate del y v with respect to x. del square v del x by del y equals del x del v by del y, which gives del xy function v. It's an interesting and important fact that the mixed derivatives do not depend on the order in which the derivatives are carried out. In other words, double derivative of v with respect to x and y equals del square v by del y del x. Exercise 1. Compute all first and second partial derivatives, including mixed derivatives, of the following functions. X square plus y square is equal to sine xy, x by y exponential power x square plus y square, and exponential power x cos y. Stationary points and minimizing functions. Let's look at a function of y that we call capital F. See Figure 1. Figure 1. Plot of the function fy. Notice that there are places on the curve where a shift in y in either direction produces only an upward shift in f. These points are called local minima. In Figure 2, we have added dots to indicate the local minima. Figure 2. Local minima. For each local minimum, when you go in either direction along y, you begin to rise above the dot in fy. Each dot is at the bottom of a little depression. The global minimum is the lowest possible place in the curve. One condition for a local minimum is that the derivative of the function with respect to the independent variable at that point is 0. This is a necessary condition, but not a sufficient condition. This condition defines any stationary point. The derivative of fy with respect to y equals 0. The second condition tests to see what the character of the stationary point is by examining its second derivative. If the second derivative is larger than 0, then all points nearby will be above the stationary point, and we have a local minimum. d square fy by d square y is greater than 0. If the second derivative is less than 0, then all points nearby will be below the stationary point, and we have a local maximum. That is, d square fy by d square y is less than 0. See Figure 3 for examples of local maximum. Figure 3. Local maxima. If a second derivative is equal to 0, then the derivative changes from positive to negative at the stationary point, which we call a point of inflection. d square fy by d square y equals 0. See Figure 4 for examples of a point of inflection. Figure 4. Point of inflection. These are collectively the results of a second derivative test. Stationary points in higher dimensions. Local maxima, local minima, and other stationary points can happen for functions of more than one variable. Imagine a hilly terrain. The altitude is a function that depends on the two coordinates, let's say latitude and longitude. Call it axy. The minima of axy. The tops of hills and the bottoms of valleys are local maxima and minima of axy, but they are not the only places where the terrain is locally horizontal. Saddle points occur between two hills. You can see some examples in Figure 5. Figure 5, a function of several variables. The very tops of hills are places where no matter which way you move, you soon go down. Valley bottoms are the opposite. All directions lead up. But both are places where the ground is level. There are other places where the ground is level. Between two hills, you can find places called saddles. Saddle points are level, but along one axis, the altitude quickly increases in either direction. Along another perpendicular direction, the altitude decreases. All of these are called stationary points. Let's take a slice along the x-axis through our space so that the slice passes through a local minimum of a. See Figure 6. Figure 6. A slice along the x-axis. It's apparent that at the minimum, the derivative of a with respect to x vanishes. We write this, derivative of a with respect to x equals 0. On the other hand, the slice could have oriented along the y-axis, and we would then conclude that derivative of a with respect to y equals 0. To have a minimum, or for that matter, to have any stationary point, both derivatives must vanish. If there were more directions of space in which a could vary, then the condition for the stationary point is given by the derivative of a with respect to xi equals 0 for all xi. There is a shorthand for summarizing these equations. Recall that the change in a function when the point x is varied a little bit is given by del a equals summation I del a by dx times del x. The set of equations 3 are equivalent to the condition that del a equals 0 for any small variation of x. Suppose we found such a point. How do we tell whether it is a maximum, a minimum, or a saddle? The answer is a generalization of the criterion for a single variable. We look at the second derivatives, but there are several second derivatives. For the case of two dimensions, we have second derivative of a with respect to x, second derivative of a with respect to y, and second derivative of a with respect to x and y, and second derivative of a with respect to y and x. The last two being the same. These partial derivatives are often arranged in a special matrix called the Hessian matrix. Important quantities called the determinant and the trace can be made out of such a matrix. The determinant is given by det h and this, and the trace is given by trh, second derivative of a with respect to x plus the second derivative of a with respect to y. Matrices, determinants, and traces may not mean much to you beyond these definitions, but they will if you follow these lectures to the next subject, quantum mechanics. For now, all you need is the definitions and the following rules. If the determinant and the trace of the Hessian is positive, then the point is a local minimum. If the determinant is positive and the trace negative, then the point is a local maximum. If the determinant is negative, then irrespective of the trace, the point is a saddle point. However, one caveat: these rules specifically apply to functions of two variables. Beyond that, the rules are more complicated. None of this is obvious for now, but it still enables you to test various functions and find their different stationary points. Let's take an example. Consider capital function fxy as sin x plus sin y. Differentiating, we get partial differentiation with respect to x, cos x, and with respect to y, cos y. Take the point at x equals pi by 2, y equals pi by 2. Since cos pi by 2 is 0, both derivatives are 0 and the point is a stationary point. Now, to find the type of stationary point, compute the second derivative. The second derivatives are: the second derivative of f with respect to x is minus sin x, with respect to y is minus sin y. The second derivative with respect to x and y is 0, and with y and x is 0. Since sin pi by 2 is 1, we see that both the determinant and the trace of the Hessian are positive. The point is therefore a minimum. Exercise 2. Consider the points x equals pi by 2 and y equals minus pi by 2. X is called minus pi by 2 and y equals pi by 2. X equals minus pi by 2 and y equals minus pi by 2. Are these points stationary points of the following functions? If so, of what type? Capital fxy is equal to sin x plus sin y. Capital function fxy equals to cos x plus cos y.